So I'm Mohammed. I'll continue with the branch prediction. This is a very interesting question and easy, straightforward, but a bit tricky. So you have to be careful about every sentence here. So you are given a piece of code, and it's basically an array of n elements. And those elements, or the value of those elements, are truly random generated. So you cannot predict the value of those elements at each index. And you have 3 if loops inside the for loop. And at each if statement, you are trying to examine if that value is multiple of 2, 3, or 6. And this is not if else. This is very important. OK. And the question asks you to show out of those 4 branches. So you have B1, which is the for loop, B2, B3, and B4, which are the if loops. So out of those 4 branches, what are the locally correlated branches? Local correlations mean here for the specific branch. If I know the previous value from the previous iteration, or if I know that branch is taken or not taken, can I decide on the current iteration whether this branch will be taken or not? So this is what does mean a local correlation. So basically, for the first branch, I have a for loop from 0 to n minus 1, which means this iteration will be repeated n times. So if I'm in the n minus 1 iteration, so I know for sure the next iteration will be taken, right? Because I have n many iteration for branch 1. But for branch 2, branch 3, branch 4, I'm trying to examine the value of the element. And the value, it says here, it's completely random. So if I know that the previous value, or from the previous iteration for branch 2 was not taken, so I cannot decide, I cannot predict for the current iteration whether B2 will be taken or not. So that's why the locally correlated branches are only B1. So for the second part of the question, the same thing, but I'm asked here to find the globally correlated branches. Meaning that if I'm the current iteration and one of the branches is taken, can I decide, can I say something about the other branches? Can I say whether it will be taken or not? So, for example, B2. So if the value at that index is multiple of 2, can I say something about it, whether it's being multiple of 3 or multiple of 6? So obviously, if B4 was taken, or it's currently taken at the current iteration, then for sure, B2 and B3 should be taken. Any number that's multiple of 6 should be for sure multiple of 2 and 3. So B4 is globally correlated with P2 and B3. Any questions so far? So very easy. Just you need to remember the difference between locally correlated and globally correlated.
I have a question.
Yeah.
Which direction should they be correlated? Because we could also say that if we took B2, we take B4. If we took B3, we also take B4. But I mean, since B4 is at the end, how can we say that if we took B4, we also take the other? Wouldn't it be the other way around?
So yeah, so this is basically based on the compiler. So if the compiler decides that B1 is placed before B2 and then B3 and so on, so when it add PC equal PC plus 4, then you go directly to the B4, then you need to predict the branch 4, whether it's taken or not. It could be the other way around. This one could be placed before, right? So anyway, the thing here is that if branch 2 and 3 are taken, then for sure branch 6 should be taken, right? And the other way around, if B4 is taken, then B2 and 3 for sure should be taken, right? Because any value that's multiple of 6, multiple of 2 and 3 as well. So straightforward. Okay, so now for the second part of the question. So this should be B or 2, and this is A. Okay. So now I want to run this piece of code on a processor that has a global branch predictor. So I have, I'm given this a global history register that has 2 bits only. So you could have 3, 4, but here I'm only having 2 bits. 2 bits mean I have 4 entries. And for the global history register, what I'm storing here is basically if 2 branches are taken or not. So it could be taken, taken, not taken, 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 not taken, and not taken, not taken, right? So one of those entries. So I'm considering 2 branches at the same time. And the pattern history table, I'm storing 4 entries as well. So for each one of those, it could direct me to this pattern history table where I'm storing something here in each entry. So I'm having 4 entries in, so this is the global history register, and this is the pattern history table, and this is the entry. So I'm setting all those values here to 0 initially. And whenever I'm facing or I'm hitting one of those entries in the global history register, so I'm trying to increment this by 1. And if it is missed, then I'm decrementing it by 0. Or if it is taken, I'm increment by 1. If it is not taken, decrement by 1. So this diagram is given the other page, which is here. Okay. So yeah. So the question now, I'm doing this for loop 120 times, means that n is equal to 120. So so the question asks me what's the value should be here in the first entry, given that the first record is taken and taken. So there are 2 branches are taken. So what's the probability of the next branch to be taken or not? Or in the other, so let's rephrase it. So what will be the value of that branch, the third one, taken? Then I'm going to increment 1. And if it is not taken, I'm going to decrement by 1. So what's the final value after 120 iterations? Okay, so I'm having B1, B2, B3, and B4. Okay, so now let's assume B1 and B2 are taken. Okay, what will be the contribution of B3 being taken or not to the total value? So for this equation, because it's given here that all the values are completely or truly randomly generated, so I cannot guess any values. So for simplicity, I'm going to assume that the values are 1, 2, 3, 4, 5, and 6. So this is my array. So any value at any element or any index can be one of those values, okay, just for simplicity. Why select 1 to 6? Because this piece of code is always examining the multiple of 2, 3, and 6. So this range should cover all the possible values. After that, I'm repeating myself. So after 6 to 12 is the same thing as 1 to 6, right? Okay, so remember that, maybe I could show it here. Yeah. So this is B1 and B2. So B1 is always it could be any of those values, right? So 6 over 6, the probability of having all those values. So it could be any one of them. I'm not excluding any one of those. For B2, it should, if I take B2, means that the number is multiple of 2. How many of those is multiple of 2? 3 values, right? Which are 2, 4, and 6. And this has the probability of 3 out of 6. Now, for B3 to be taken means that one of those number, or all of them, or some of them, is multiple of 3 as well. How many of those is multiple of 3? Only this guy, right? Okay, so which is multiplied by 1 over 3, which is 6 out of 3 values, right? Clear? Okay, great. Now, this is for the first case where B3 is taken. Given that B1 and 2 is always taken based on the entry here. So both of them are taken. Now, for B3 to be not taken, which is the other two values. So 3 out of 6 multiplied by 2 out of 3. So this is taken, this is not taken for B3. So now what's the total? Again, should be in plus, this should be in minus, because I'm decrementing whenever a branch is not taken. So do the math, you will get, minus 1/6. Any questions so far? Just add them together, that's it. Simple math, right? Okay, so now I'm considering the other possibility where I'm having branch 2 and 3 are taken, and I want to examine if B4, the contribution of B4, whether it's taken or not taken. So B2 and 3, it's multiple of 2 and multiple of 3. So I want to check out of those 6 values, how many of those are multiple of 2 and 3 in the same time? How many? Okay, so which is number 6. So I'm having 1 out of 6 is both for branch 2 and 3 to be taken. And now I'm checking the branch 4, which is multiple of 6. So we already said that I'm picking this guy, which is number of 6. Now what's the contribution of B4 to be taken, which is single value, which is 6. So always 6 will be taken, right? So multiply by 1, that gives me 1 out of 6. Now, what if B4 is not taken? If B4 is not taken, means that there's no other values. I'm having only one value. So that's why minus 0. And I'm having 1 out of 6. Now, you can consider the same thing for B4 and B1, which are taken. And in this case, multiple of 6 is only 1 out of 6. Now, I'm checking if branch 2 is taken. Branch 2 is taken mean I have only 6, the value 6. So it's always multiple of 2. That's why we multiply it by 1, we get 1 out of 6. And we have no decrement, no possibility for B2 to be not taken. So it always should be taken because any value is multiple of 6 is multiple of 2 as well. And the same thing, so what's remaining now? I'm having B1 and B2. Both of them to be taken. B2 is multiple of 2. How many of those are multiple of 2 is 3 out of 6. Multiply by... No, the first one was B1 and B2, and I'm checking B3. So here I'm checking B1 and B2. Oh, sorry. Yeah, so first one was B1, B2. I'm checking B3. Now B2 and B3, I'm checking B4. Now B4 and B1, I'm checking B2. And what else? So it should be B2 and B3. And now I'm checking B4, right? Okay, now it makes sense. So B2 and B3 is multiple of 2 and 3. We have only one value, which is 1 out of 6. And now I'm checking B4, which should be 1, the single value. Then I have 1 out of 6. Now, 1/6, 1/6, 1/6 is 3/6. Minus 1 out of 6, this gives me 2/6, multiplied by the number of iteration, 120. So this is do the math, you get the value.
Let's see. Okay, so this this problem deals with a couple of figures here. So figure 1 shows a systolic processing element, right? And so figure 1, figure 1 is this guy here. And so this is one processing element. And we're told that each processing element takes in 2 inputs, which are N and M, and then it has 2 outputs, which are P and Q. And then every processing element also contains an accumulator called R, which is just like a data storage element. And this can be read from and written to. And the initial value of the accumulator is 0, right? So figure 2 expands upon this and shows an array of these guys composed of 9 elements. And figure 2 is this one. So we have 9 of these processing elements here. And then these are going to be input data tokens. So we have that array of 9 processing elements. And so we want to program this systolic array design to perform the following matrix multiplication. So we want the output C to be the matrix A times the matrix B, right? And so the matrix multiplication is, just like row times the dot product of like row times column, and then row times column to produce all the output elements. And so we have a bunch of like design specifications here. And so in every single time cycle, every processing element, which is this guy down here, will take in the 2 inputs, perform a particular computation, and then write the outputs. And the time cycle labels on the input boxes determine which time cycle the inputs will be fed into the processing elements. And so that means that over here, 0, 1, 2, 3, 4 mean like these data elements will be sent in here on cycle 0, and these on cycle 1, and these on cycle 2, and so forth. And same with these inputs coming this way, right? So every processing element takes in those inputs. And so any processing input element that is not driven will default to 0. And any processing element that has no output arrow will also have its output ignored. So the output from these guys is just basically discarded. And any input that we don't actually specify is just going to be 0. Okay. So after all the calculations are finished, each processing element's accumulator will hold 1 element of the final resultant matrix arranged in the correct order, right? So we want this output matrix, which is the 9 elements of C, to basically be encoded in these guys. And we can assume that the correct order is basically the same order as the input, and as the same order as stated here. And if we assume something else, then we should just say so. So we're going to go ahead and assume the same order for this case. So we want C00 to be here, C01, C02, and so forth. Okay, so yeah, we want that output at the end. So the question asks us, please describe the operations that every individual processing element performs using mathematical equations and the variables mn, p, q, r, which are the input outputs and the register here. So they give us empty fields for what should P be, what should Q be, and what should R be as a function of the inputs and R. All right? And so the second part asks us, please fill in all 30 input boxes so that the systolic array computes the correct matrix multiplication result described in the previous page. And the hint says to, you write it in terms of A, ij, and B, ij. Okay, so I'm going to leave the matrix up here. And then we have our diagram here. So it's okay, it almost fits. But yeah, so basically we want to arrange all these inputs of A and B into these input boxes such that this computation is performed correctly, right? So suppose that because we want the outputs to be like this, we will take a look at the first output, C00. So we know C00 should be composed of the dot product of this first row times this first column, right? And so we want A00 times B00 plus A01 times B01 plus A02 times B20, right? So we somehow need to feed those inputs into this box. So these A and B are going to have to go either here or here and be fed into here 1 per cycle, right? And so for the next processing element, for example, C01 is over here. And so we're going to want this series of A's, but then the next column. And so all the same A inputs need to go to this box, and also by the same logic, this box. So it would make sense to feed the A inputs this way, right? Because those are going to be used by all 3 of these processing elements. Likewise, for the B processing elements, we're going to use them for C00, C10, and C20, right? Because for C, C00, C10, and C20 will be the dot products of these rows times this particular column. So it would make sense to put them down here. So now it's a question of how we want to arrange the logic such that the output operation will be correct. So if we're passing the inputs from basically the same inputs are being passed to each of these three processing elements, right? In any direction we really think about. And so the same input element that comes in here, which is M, is also going to be the output element, P. So these two are identical. You don't perform a transformation on the input for this particular output. And the same goes for N and Q. So if we're just passing the elements through, then when we come to our equations here, we're just saying P equals M, because it's just a pass-through, and then Q equals N. And that's all that's going to happen. And then in order to perform the dot product, every cycle that we have two of these elements come in, we're going to have to perform element times element, and then accumulate the result, right? Because so every cycle we're going to get a new set of inputs. We're going to multiply them and add them to the accumulator. So what we really want is R equals the original R plus the inputs, the product of the inputs, M times N. So these are the operations that the processing elements will perform individually, right? And so the last part of this question is to kind of figure out how to organize the data such that we get this computation performed correctly. So, okay, so we can think about this in terms of at what cycle the inputs will reach particular elements. So for this first element, in the initial, the very first cycle, we'll have data to compute with. So we want to put the first elements we can here. And so we can put elements here and here, and the cycle after, and the cycle after. And since there's only 3 we want to do, we can just leave nothing in the outer 2 cycles, right? So we can just have 0 inputs here, because we don't need to do anything. For this guy, it'll receive an input on the very first cycle here, but it will take 2 cycles to receive an input here, right? So we don't want to put a data element here, because otherwise we'll just have 1 input and then nothing here. So instead, we're going to pass the input from the second cycle. That way, when this one reaches this processing element, this one will also reach this processing element, and we'll perform the correct product. So we're going to have 0. And then by the same token here, it's going to take 2 cycles, so like 1, 2, 3 to get here. And so we want this data to also take 3 to get here. So we're going to have data here, meaning that these two will be zeros. And so by the same logic over here, it's going to take 2 cycles to get here. So we want this data element to come in at the same time as this one. So we're going to put 0 here and also here. So now we know we want to arrange our data basically in this fashion and then this fashion over here. And so we just have to add these inputs, right? So on the very first cycle, we can have this guy compute A00 and then B00. And then on the second one, we can have it do A01. And then over here, we can have it do B10. And then so forth. Sorry, is it off the edge? Oh, yeah, okay. So at this point, we're basically done with the problem. We're just filling in this table in terms of like at what cycle the inputs get here, right? So A00, A01, A02, and then here B20. And then for this guy, he's going to be computing the product of the first row, which comes in, I guess I got A and B backwards. Yes. Very good. Yeah. So, okay. So I'm just going to write this again. So this is A00, this is A01, this is A02, and this is B00, B10, B20. Okay, yeah, so this guy's going to take in the 3 A's afterwards, and we're going to require the second column of B's here. So this is going to be B01, B11, and B21, and then so on and so forth. We just fill in the table, yeah? Okay. So yeah, that's both parts of this question, and if you just fill in the rest of this. So any questions about this one? I think it's a lot more straightforward than some of the other ones. So yeah, okay, yeah. I guess we have a solution sheet. So there you go. It's done.
So this is like typical question in which you have to calculate what's the SIMD utilization. Remember that the SIMD utilization, not only in GPUs but also in vector processors, mean like the ratio of lanes that you are actually using. So here, the first thing that you have is the definition. SIMD utilization of a program run on a GPU is defined as the fraction of SIMD lanes that are kept busy with active threads. When are we going to have active threads? Well, we're going to have active threads when we actually execute some instructions for these threads. The question gives us some piece of code, and this is essentially a for loop, as you can see. And it says that this is going to be executed on a GPU. So the way that this is going to be executed on the GPU is distributing the iterations of this loop across the threads that we have in warps. So here we have n iterations, and these n iterations are going to be executed by a certain number of warps. That's the first question, that's part A. How many warps does it take to execute this program? Please leave the answer in terms of n. So we have n iterations. We know that the warp size is 32. A warp in the GPU consists of 32 lanes, and we also have 32 threads, and we also have 32 SIMD lanes in the GPU. So n divided by 32 is the number of warps, because so in case that n is not divisible by 32, we have to use the ceiling of this division, right? Maybe the last warp is not completely busy, but we will steal this number of warps. Part B says, assume integer arrays A. So we have A and B. A has a repetitive pattern with 24 ones, so it will be something like this, 24 ones, followed by 8 zeros. And B have a different repetitive patterns which have 48 zeros followed by 64 ones. What's the SIMD utilization of this program? So observe that this is the repetitive pattern of A. And A, the values of A determine if the body of this if statement is executed or not. As you already know, this if statement will be converted into some kind of comparison and some kind of branch, right? Because in case that you don't need to execute this body, you will have to branch in order to avoid this loop body. So that's why depending on what's the exact value that each of the 32 threads of the warp read, we will execute the body of this if statement or not. And observe that here the condition is that A is divisible by 3. Because all these 24 ones that we have here are not divisible by 3. Only those threads that read I equal 0 will actually execute this statement here. So if we have two instructions, instruction 1 and instruction 2, the first instruction for sure is executed by 32 threads, but the second in each warp, right? But the second instruction, instruction 2, is only executed by those threads for which A modulo 3 is equal 0. That is, for these 8 threads that read these 8 zeros here. So, out of 32 plus 32, that would be the maximum number of threads that we have executing this instruction 1 and then instruction 2, threads that belong to the same warp. The SIMD utilization in this case is 32 plus 8 divided by 32 plus 32. So this is 40 divided by 64. So that's the answer to this part B. The second part says, is it possible for this program to yield SIMD utilization of 100%? Well, and the answer is yes. But this case in which the SIMD utilization is 100% is going to be dependent on the value of each of the elements of array A, as you already know. There are two possibilities here if we want to have 100% SIMD utilization. The first possibility is that all threads in each warp execute instruction 1 and then they go into the body of the if statement and they execute instruction 2. That's one possibility. The other possibility is that the threads in the warp, all the threads in the warp execute instruction 1, but they don't execute instruction 2 because this if condition is not true for any of them. So the answer in this part, if yes, what should be true about arrays A for SIMD utilization to be 100%? The answer here is two possibilities. Every 32 elements is divisible by 3, or every 32 elements isn't divisible by 3. So either way, we will have all threads in the warp executing both instructions or only executing one of the instructions. We are going to stop here because we run out of time. The rest of the exercise is very similar. You already know how you have to reason about this exercise. Here there is a question, part D and E are very similar questions, but the percentage, the SIMD utilization is different. You can reason in a similar way. And the very last part is actually quite easy. This is what we explained in the first GPU lecture about dynamic warp formation. You might remember that there might be a way of, let's say, merging warps like this, where some threads are active, other threads are not active, and if these threads that are active are not in different warps, are not in the same lane, they can be merged, and this way we can have more efficiency in our execution. We stop here.
Okay, so we have a question about tracing the cache. So we spent a little bit of time looking at caches, and so this goes over some of the more fundamental concepts of caching, right? So in this problem, we're saying that we have 3 types of CPUs. We have the 6808D, T, and F, okay? And all 3 of these CPUs feature one level of caching. So the system looks sort of like we have a CPU here, and then we have an interface to a cache, and then the cache interfaces with memory. And so each one of these CPUs has a different type of cache, right? And so we're given that the cache size is 128 bytes, and the cache block size is 32 bytes. So that tells us that precisely four blocks fit in one of the caches, right? And we also know that the cache uses the least recently used replacement policy. So the only difference between these 3 caches is the associativity. So we're given that D uses a direct mapped cache, T uses a two-way associative cache, and F uses a fully associative cache. So if we go ahead and draw these out, then we're saying that D is a direct mapped cache, so every single block, it gets its own set, right? So we have 4 different sets in the cache, and there's only one way. The design T uses a two-way set associative cache. So we know that there's 2 sets and 2 ways because there's precisely 4 blocks in this cache. And then cache F has a fully associative cache, so there's only one set which contains all 4 blocks. Right? So when when each of these caches store a block, in D, it's mapped directly to only one set. With T, it's mapped to one of these sets, but it could go in either way. And with F, all blocks are going to be mapped to this one set, but they could occupy any of these ways. Right? So we have these 3 caches. So then we're told that we run this particular program to evaluate the CPUs. And this benchmark tests only memory read performance by just issuing a series of reads to the caches. And so we're going to assume that the caches are empty before we run the program. Okay? So the cache accesses that are generated by the program are as follows in order of access from left to right. So we have a sequence of accesses to a bunch of different blocks. So these are accesses to the cache by the program. So they're what's going on this bus. So every single letter here represents a unique cache block. And all 8 blocks are guaranteed to be contiguous in memory. However, the ordering of the letters does not necessarily correspond to the ordering of the blocks. So it's a mystery for us to solve. We don't know how these fit together. And then we're given that for the D cache, the direct map cache, we observe the following sequence of cache misses in order of generation. And so the cache misses are when the CPU requests from the cache, but the data does not exist in the cache, and so the cache has to go out to memory to get the data. So the misses are what's going on this bus. And so by using these above traces, we want to figure out which cache blocks map to the same set for the 6808D processor. And so we can say a couple of things right off the bat. So we have 8 cache blocks that are contiguous in memory, but we only have 4 locations in the direct mapped cache. And so by looking at some of the bits in the address, these cache blocks will be mapped into precisely one of these 4 sets, right? So given 8 fitting into 4, we're going to have 2 cache blocks mapping to each set. And so we're basically looking for pairs of cache blocks that belong to each set. So we have the sequence of accesses and we have the sequence of misses, so we can begin taking a look at how to go through this. So let's draw out an empty cache here. So this is what our cache is going to look like at the beginning of the program with nothing in it, and these represent the 4 different sets. So at the beginning of execution, we have this sequence of accesses, which starts with A, and we have this sequence of misses. And so when the program first requests A, it doesn't exist in the cache, and so we generate a miss, which makes sense because it wasn't in the cache previously. And we don't know where it belongs in which order, but we know that it's going to be in one of the sets, so we just assign it a location. So this A generated this miss. Then we have B, and B also generates a miss because it hasn't been seen in the cache yet. But we don't know where it goes because it could be in the same set as A, or it could be in a different set, so we're going to leave it alone for now. Then the program requests A again, and A appears to generate a miss. And so this means that A was kicked out of the cache when B was brought in, because B has been the only thing in between. And so that tells us that A and B have to belong to the same set, because when B was brought in, A was kicked out, and then A comes back in, and A generates another miss. So this sequence of misses comes from these guys. Then we bring in H, and H generates a miss because it's not in the cache yet, and so we can arbitrarily assign that a location. Note that you can't put H here, right? Because we already said that there can only be 2 cache blocks per set because these blocks are contiguous in memory. So then we bring in B, and B appears to generate a miss, which makes sense because A was the last thing that was brought in. Then we bring in G, and G generates a miss, which again makes sense because it's not in the cache, but it's the same problem. We don't know where to put it, so we're going to leave it alone for now. Then we bring in H. Oh, sorry, we don't bring in H, but we try and access H. And H does not generate a miss. So that means H is already in the cache, and when we brought in G, it did not kick out H. So G has to belong to a different cache set. Otherwise, H would have been kicked out and it would have generated another miss. So G is responsible for this. H and H are both already in the cache, so they're just hits in the cache. Then we bring in A, and A generates a miss, which is true because B was brought in previously to kick it out. So then we have E, and so E generates a miss because we haven't seen it, but we don't know where it belongs. Then we call H. We try and access H, and H does not generate a miss. The next miss is actually D. So H is still in the cache. So we know that E must go either here or here, but we're not sure which yet. Then we access D, and D generates the miss. So yeah, D has not been seen in the cache, so we're not really sure where it goes either. H is the next access, and it generates a miss. So we know something kicked out H. But the thing that kicked out H could not have been E, because we've already shown that E cannot belong to the same set. So that means that this cache miss from D had to have kicked out H. Otherwise, H would not have needed bringing back in. So D has to be there. Then we try and access G, but G does not generate a miss. And so that automatically tells us that G is still in the cache, and so E has to belong here. Okay? And so G is a hit. Then we have C, and C does generate a miss. And so C has previously not been seen in the cache, so we also don't know where it goes. Then we have another access to C, which is a hit because it's already there. And then we bring in G, and we see that G is a miss. So G has been evicted in the past, and the only thing it could have been evicted by is C. So G has to belong with C. And finally, the only thing that we have left is F. So at this point, we know which cache blocks belong to the same set, right? And so this is our solution. So we can say A and B belong together, H and D belong together, G and then C, and then E and F. Right? So we've solved part A at this point. Are there questions about this part before we move on to the next one? Okay. So part B asks us to write down the sequence of cache misses for the F processor in order of generation. And so F is our fully associative processor, and our fully associative cache. And so we know that in the fully associative cache, every single one of these cache blocks will map to just the only set there is, but it can occupy any of these positions. And we're also told that the cache uses an LRU replacement policy, right? So we know which ones get evicted when an eviction occurs. So, can I get another paper? Okay. So we're going to go ahead and trace out these cache misses in their order of generation, right? And so we're basically just going to enumerate how all this happens. So we're going to draw a sort of just a model of what's currently in the cache. And so we have one set which contains 4 different ways, and we know the sequence of accesses that occur because it's given to us. And so we're just going to go ahead and go through one by one and simulate what's happening in the cache as we go. So I'm just going to transcribe this sequence really quick. So we have, just copying this down. Yeah, so that's probably enough to get going. So this is the sequence of program accesses. And so we can just begin simulating this cache. So the first A gets brought into the cache, and so it's a miss. So I'm going to denote that by putting an X underneath it. B gets brought in. It's also a miss because it doesn't exist in the cache, but we put it in a different way because there's free space. So that's a miss. A is a hit in the cache because it already exists here. So that's fine. H is new, so we put it here and mark it as a miss. B is already in the cache, so that's fine. G is not in the cache, so we bring it in, and it's a miss. H is already in the cache, already in the cache, already in the cache. So this is a more interesting one. So we have E, which is not in the cache right now. So it's going to be a miss, but we have to figure out where in this cache, what gets evicted in the cache. And so this is where the replacement policy comes in. So least recently used means we're looking for the cache line that hasn't been accessed, right? The oldest cache line, essentially. And so we can basically look backwards to see what's the oldest one that's currently in the cache. And since everything is kept in the cache up until now, we look at A, so A is in the cache, H, G. These 3 are all in the cache, and they've been recently accessed. And the least recently accessed one ends up being B, because it's the farthest. And so B gets evicted, and instead we put in E. So E is now in the cache. Then we have an access to H, which is a hit. And then we have D, which is not in the cache. So again, we have to choose something to evict. And based on the LRU policy, it's going to be not H, not E, not A, but G. So G gets evicted, and we replace it with D. And so that's a miss. Then H is still in the cache. G is no longer in the cache because we just evicted it. So now we have to pick what to evict next. So the least recently used, again, not H, not D, not E, but A. So A gets evicted, and we replace it with G. And G is a miss. C. So yeah, basically you just repeat this process for the whole set, for the whole set of accesses that we have, and you write these down in order here. And that's basically the solution for part B. Should I actually go through it all? Does anyone want me to actually go through it, or shall I move on to the next part? No? Okay. Yeah, so it's just a process of manually simulating what's happening. Okay. So the next part says that for the T cache, and remember that the T is the two-way associative cache, we observe the following 5 cache misses in order of generation: A, B, H, G, and E. But unfortunately, our evaluation setup breaks before we can observe all the cache misses that occur. So using just the given information, which cache blocks are in the same set for this processor? So now we have very little information to go off of, but we have to reconstruct what's in this cache. So we actually have some information from the previous part as well, too, because so we know that these pairings already map to the same cache sets for the direct mapped cache. So A, B, H, D, G, C, and E, F. And what this tells us is that since these 8 are guaranteed to be contiguous in memory, we know that for the two-way associative cache, if A and B conflict here, that means they have a spacing of 4 addresses between them. And here, they'll also conflict in the same set, because by being 4 away, they're also going to be mapped to the same set in the with 2 sets here. So A and B will belong to the same set. H and D will be the same set. G, C, and E, F. So the same pattern is here. So we can use that information in combination with these 5 cache misses that we're given to figure out which ones map to the same set. So I'm going to draw an empty two-way set associative cache here. And we can go through and do the same process and figure out what's going on. So over here, let's see. Should I write this down again? I don't know. Do you think it's necessary? So we have our sequence, which is A, B, A, H, B, G, G, H, A, okay. So and so forth, that maybe we'll need more later. But so okay, so we observed these cache misses. So we're basically going through this process of simulating this cache again. And so so A. So the first program request is A. And so A is going to be brought into one of these sets. And so we just assume the first one. So A happens. Then B. And ordinarily we wouldn't really know which set B should go to. But because of the information from part A of this problem, we know that B should go to the same set. So B will be mapped in here, since we're a two-way set associative. Then we have an access to A again, which is going to be a hit. Then we have H. So we don't actually know where H is going. And so we have to look at the misses that we get. So H is a miss because it hasn't been seen before. Then we have B. And so B does not generate a miss. And so that means B was not evicted. But B was also not the LRU here. A was the LRU. No. Okay, sorry. Yeah. B is the LRU. And so B would have been evicted by H if it mapped to the same set. But it wasn't, because B did not generate an additional miss there. That tells us that H maps over here. And by default, we also get that D maps over here. So that misses H. Then B is a hit because it's still in the cache. G comes in, and G generates a miss. So G, we're not sure where it goes. H and H are still hits, so that's fine. So G could still be here, and it also could have evicted the LRU, which in this case the LRU is B. So then we have an access to A. And so A does not generate a miss, which is fine because the LRU is B and A is still in the cache. Yeah? So then we bring in E, and E generates a miss. So E also gets mapped to one of these that we're not really sure which one. But we note that G and E come from different pairings. Then we have H, which H is already in the cache. This is... yeah, I think I missed something here. So... yeah, B...
that means G wasn't on the first set, it was in the second one.
that means G.
G is right next to G.
Yeah, G is required to be here because A did not generate an additional miss. Before E, yes. So G is guaranteed to be here. And so that means C is also here. And H is paired with D, so D also maps to the set. And then the only pairing left is E and F, which have to go here. So that basically gives us our different sets here. So we know the cache blocks that map to these sets are then A, E, B, F, and then H, D, G, C. Okay. Yeah, so let's go through this again. This one's a little interesting. So I'm going to do the same thing we did before, where I'm going to write this down here, and we're going to trace the misses. So we have A, B, H, G, E, which are our sequence of misses. Okay, so we start off with an empty cache. So we bring in A is a miss. We bring in B is a miss. And we know those go here. Then A is a hit because it's here. And A is now the LRU, right? So we've got to keep track of that. Then H comes in, and H generates a miss. So H gets brought in, but we're not exactly sure what H gets brought into. However, B is the LRU at this point, and B, so the next access to B does not generate a miss, right? That means B is still in the cache. And B would have been evicted if H was mapped to this set, right? Because B is the LRU. So that guarantees that H has to be down here, right? And so we know that from these pairings up here, this gives us more information that we know D is in this one too, right? So after that, B is a hit because B is still here, and now A is the LRU, right? So I'm just going to write that down. A is the LRU right now. And then we have G. G generates a miss, where we're not exactly sure where G comes in. So G could be in either still. So G. Then we have an access to H. And H does not generate an additional miss, right? So H is still in the cache. So H and H are hits. So these two are hits. Then we have A. And A does not generate a miss, right? Because the next miss is E. So we know that A is still in the cache, which means that anything new that had been brought into the other set. So what we've seen now is that G. So we know that G has to be here, because otherwise it would have evicted A. And then the next miss we see is E. So this gives us A, B, H, and G, which is basically enough information to put everything together at this point. So A and B are here. H goes with D. So H and D are here. G goes with C. So H, G, D, C are all in the bottom one. And then the only ones left are E and F, which have to be up here because, again, like these 8 blocks are contiguous, right? So that's how we get these results: A, E, B, F, H, D, G, C. Yeah. All right. Was that clear to everybody? It's a little more confusing than the first part, so like takes more thought. But yeah. Why D belongs to H and G? Because so if we look at like what the addresses actually are, right? Let's say that 3, 4, 5, 6. So we know that A, B, C, D, E, F, G, all those letters fit into this 8 contiguous memory segments, right? So the 8 contiguous memory locations. So like we can just think about this being like, I'll give an example, I guess. So we could just think about, sorry? Oh, yeah. Okay, but it's all about like, you know, A and B would have to be off by 4, right? In order to map to the same set over here. Because you're using specific bits of the address, right? So it's like modulo 4. And here, this is modulo 2, which anything that's modulo 4, it's going to fit into here. And they're going to map to the same set here as well. So yeah, it's pretty important that the 8 are contiguous, because if they weren't, then you have no way of really knowing anything. Okay, so the next part of this question asks you to write down the sequence of cache misses for the T processor in order of generation. So we essentially follow the exact same prescription that we did here, where we go ahead and simulate the cache, except this time we're simulating the T cache, given that we know which one's mapped to which set. So should I do this or should I skip it? Because it's literally the exact same thing. You just go one by one and track whether it's a hit or miss, and then you just simulate the state of the cache. Yeah. Okay. So I'm gonna skip that. So does anybody actually want me to go through it? Like, just raise your hand or something, because yeah. Okay. So I'll skip that one. So then, the last part of this question asks you, what is the cache miss rate for each processor? So they're asking us for D, T, and F. And so we've already done all this work, actually. So if we go ahead and look at this sequence right here, we know exactly how many hits and how many misses we get. And they give it to us for the direct mapped cache, so we don't have to do that. We now know it for the fully associative cache, and we would have just done it for the two-way cache. And so we have all that information. So we literally just count up how many misses we have divided by how many total program accesses there are. And it just gives you a number. Right? And so that would be the cache miss rate. Okay. Yeah, so that's the end of this question then. So yeah, do you guys have any questions, or should I move on to the next one?
So question 2 is cache performance analysis. In this question, what we do is do some micro benchmarking. This means that we are going to execute a specific program, short program, that is going to exercise some particular features of the cache hierarchy. It's very interesting. This kind of micro benchmark is very useful because it usually allows us to do some reverse engineering in systems that we don't know how exactly they are built. And after getting this knowledge, we might be able to optimize our code, for example, better. So as you can see, for this micro benchmarking, we are given two codes, code 1 and code 2. And we are going to access in these codes to one array data that contains 4-byte elements. So it's 32-bit unsigned integers. There is a note here that says, in order for you to know, don't care about that this latency array, the accesses to this latency array where we are going to store the latency of each memory access is not cache. So these accesses bypass all the caches. And timer, as the question says, it's going to return a timestamp. So if we go through code A, we will see that we go through the array data with a certain stride, and we record the timestamp in the right before the memory access and right after the memory access, and then this way we calculate the latency. In the code number 2, we have two loops. The first loop is similar to code 1. Actually, both loops are the same. The only thing that changes is the size that we are accessing. Here is size 1, and here is size 2. With the stride 1 or with the stride 2. As you can see, is in this loop 2 where we are going to measure the number of cycles that we need. As the question says, the cache hierarchy has 2 levels, so we will have our CPU, L1, L2, and main memory. And we also know that the size of this L1 is 4 kilobytes. Part A says that we run code 1 and we obtain this chart that you can see. You can see in the screen. So in this chart, what we can read is the latency of every memory access for 64 memory accesses. Keep in mind that these memory accesses, the stride in these memory accesses is 1. So stride is equal to 1. What happens here? This part of the question asks about the cache block sizes in L1 and L2. So what happens here? We should infer what happens from the latency values that we see in the chart. As you can see in the chart, there are 3 different latency values, 700, 300, and 100 cycles. So these give us an idea of which part of the memory hierarchy is being accessed. Obviously, L1 is closer to the CPU than L2, and L2 is closer than the main memory. So it is expected that this lower latency, 100 cycles corresponds to L1, the 300 cycles correspond to L2, and the 700 cycles correspond to the main memory. And actually, exactly what happens here in the very first access, when I is equal 0, we will have an L2 cache miss. For example, this cache block in memory will be brought to L2 and also to L1. And because we have an L2 cache miss, that's why we see this latency of 700 cycles. Keep in mind that the next access is with a stride equal to 1. So it's exactly it's exactly the next 4 bytes. The next 4 bytes that are also in the same cache block. So that's why we see this shorter latency of 100. And we see the same latency for the next 7 accesses. And right after that, 300. The latency is 300. So this gives us the answer actually for at least for the cache block size in L2, which is for 8 memory accesses is 32 bytes. So in L1, we are using blocks of 32 bytes. What happens in L2? Observe that memory access with I equal 8 has a latency of 300, so it's hitting L2. And then we again have 7 accesses to L1 because the latency is 100. So this means that another L1 cache block is being fetched from L2 to L1 with this memory access number 8. That's why we have then 7 hits. And then we have again an L1 miss and L2 hit. We are another L2 hit here, and here again we have a miss in access number 32, which is 128 bytes. And that's why we can infer that the L2 cache size is 128 bytes. Is it clear? Okay. So then let's move to part B. In part B, the question is, we are using code 2 with stride 1 equal to stride 2 equal to 32. Size 1 is 1056. You have one question? Part A. So actually, we expect from you that you answer. You explain briefly what this is about. You know, it's not just saying 32, 128. Yeah. Okay. And as I was saying, in part B, size 1 is 1056, size 2 is 1024. And in this case, we observe that latency 0 is equal to 300 cycles. Keep in mind that latency 0 is the value that we obtain in this array latency for the very first access in this second loop. So latency 0 corresponds to I equals 0. So the question continues, says, however, if size is equal to 1024, latency 0 is 100 cycles. And the question is, what is the maximum number of ways in L1? Okay, we can assume that the replacement policy is FIFO or LRU for now. So we know that because we know the size of the cache, we know that there are 128 blocks in the cache, and we also know how we are accessing this array data, right? So let's say that this is our array, and with a stride, and each of these rectangles represents one block, one cache block. In the first pass, in the first loop of code 2, we are accessing with a stride 32, so this means that we read this element, this element, this element, and so on. And the question says, if the size of the array is 1056, if we are accessing up to 1056 elements, or size 1 is equal 1056, we are going to obtain latency equal 300 cycles. Observe that here, this is 1024. Observe that here we have 32 cache blocks. So the reason why we measure latency 0 equal 300 cycles when size 1 is equal 1056 is because this last cache block is replacing cache block 0. Okay? So that's why we miss in L1, but we hit in L2. In case only, this part of the question, in case only 32 cache blocks are accessed, because size 1 is 1024, this cache block is not being accessed, so it is not replacing cache block 0. So that's why we hit when we access element 0 for the second time. So from this, we infer that the maximum number of ways is 32. Okay? Fine. If you don't have any questions, let's discuss part C. So in part C, we again use code 2, and we are also going to use code 1 after that. And what we want to figure out is what is the replacement policy. We already know that the replacement policy is going to be FIFO or LRU, because that's what the part B told us. But we don't know exactly yet, so that's why we run this different experiment where we first run code 2 with stride 1 equal 32, size 1 equal 1024, stride 2 equal 64, and size 2 equal 1056. So now, in our array data, something like this again. This is 1056. 1024, this is 0. So in the first pass, in the first loop of code 2, we are accessing this element, this, and so on. Recall that we know the question tells us that the associativity is the maximum obtained in the previous part, in part B, so we know that the associativity is 32, right? So as I was saying, in the first loop of code 2, we are accessing these elements. In the second loop of code 2, now the stride is 64. So this means that we read here, and here, here, and so on. So observe that after running code 2, we run code 1, again with a stride 32, and again with size 1024. And we observe that latency 1 is 100 cycles. Latency 1 is the latency of this memory access in code 1. So if it's 100 cycles, this means that we find this cache block in L1. So even though this cache block was not accessed in the second loop of code 2, it is still in the cache. So it has not been replaced. So that's why we know that this cannot be LRU, because if it were LRU, it would have been replaced, and the replacement policy is FIFO. Is that okay? Okay. So if A, B, and C was clear, if you understood L, B, and C, then part D must be easy for you. It says, now we carry out 2 consecutive runs of code 1 for different values of size. 2 consecutive runs. In the first run, stride is equal to 1. In the second run, stride is equal to 16. We ignore the latency results for the first run and average the latency results of the second run. We obtain the following graph. What do the 4 parts shown with the arrows represent? So keep in mind that in the first part, in the first run of the code, caches are called, and we are going to warm them, right? We are going to load cache blocks in the caches, and after that we run the same code for the second time. So we are going to find some hits and misses, right? So some of the cache blocks will be in L1 or will be in L2. We might find them or not. So we will see. Observe also that the interesting part here is that we don't know exactly what's the size of the caches. Well, we know that L1 is 4 kilobytes because the question is giving us this information, but we don't know what's the size of the cache, and you obviously don't have it here in the H label. So, but it's something, it's clear. Here, latency in this part, first part, before arrow 1, the latency is 100. Between arrow 2 and arrow 3, the latency is 300. And after arrow 4, the latency is 700. So it is clear, and also keep in mind that in this plot, in this graph, we are averaging the latency results of all the memory accesses. This means that all memory accesses here hit in L1. Here we find hits in L2, and here misses in L2, and we should access main memory for all the memory accesses. So what happens in this part, even though in all these experiments, in all this flat part of the curve, in all these experiments, we have latency equal 100. What happens is that the size of the array that we are accessing is smaller or equal than the cache size, right, than L1. So you can be sure that this point here, that arrow 1 indicates, is 4 kilobytes. So this would be a good way to know what's the size of L1. That's exactly the same for arrow 3. This is the size of L2. So this experiment is good to know what's the size of L2, right? Or to confirm what's the size of L2 if we already knew that. And in these parts between arrow 1 and arrow 2 and between arrow 3 and arrow 4, what happens is that some cache blocks hit. So we have hits for some cache blocks. We have misses for other cache blocks. That is also related to the replacement policy that we are using. And the larger the larger the array, the more cache misses that we have in L1 or in L2. Okay? So that's all, if you don't have any questions. Okay, I guess it's clear.
So there is a sort of a story of the question, but let me quickly summarize it for you. So basically, here in the question, we have an architect who is trying to build a specific machine for high-frequency stock trading, right? And here are the two processor designs that this architect is considering using in her system. And here's some more information about like what is known for these processors. But one thing that is unknown is the cache hierarchy or the memory subsystem. And this question is basically asking us to figure out what is the cache hierarchy based on some experimental data. And so basically this architect is running this application shown with this code over here to figure out those details of the microarchitecture. So the program here is simple. It is basically doing random accesses over parts of the memory. And there are two inputs to this program. One of them is the stride, and one of them is the max address. So when you look at the code, we see that so there's a sort of an infinite loop, like it loops for n times. So first, the address, this like variable is set to some random data, and then multiplied with the stride and modulated by max address. So what this means is, if you, for example, have stride to set 1 and then max address set to 4, no matter what random data is generated here, the outcome will always be like accesses to address 0, 1, 2, and 3, okay, in any order, in random order. And then when the stride is 2, for example, and max address is still 4, then the program will only randomly access 0 and 2, right? So you can like figure out what will happen when you change the stride and max address in different ways. But at the end, like what happens with this application is you just like randomly access specific addresses in the memory. Okay, and yeah, as I said, the question is to figure out like what is the, for example, the size of each level in the cache hierarchy, what is the access latency to it, details like that. Okay, let me see if I missed anything here. I don't think so. Is the question clear? And one more thing that I have to, I will emphasize is that this application runs for a very long time. So here assume n is something very big. So like the cache is warmed up, and what you observe in the data that I will show next is that state, like when the cache is warmed up completely. Okay. And here in this part, we see some data obtained by running this application for this processor over here. And in the x-axis, we see how the max address changes, and different lines here show different strides. So strides 1, 2, 4, and 8 overlap here on the same curve. And then here we have stride 16 and stride 32. Okay, so it is like difficult to read this at first, but if you like go through it carefully, it's not difficult to understand. So here, in this question, like one thing that you have to figure out to like quickly solve this question is like you have to basically understand, right? So you have to understand how caching works, how like how access happens, and how like data is brought from the main memory to different levels of the cache, and how they interact with this subsystem, right? So for example, when you have a cache hit, you'll have some like lower latency compared to a cache miss. And this will change depending on how far in the hierarchy you go through the misses, right? So let's say if you have 3 levels of cache, if you miss in all of them, you will have the largest latency when you go to the main memory. Okay, so, and here in the table are the parameters that we have to fill in. So there are some stuff that we cannot determine and some stuff that is not applicable. So you have to fill this table accordingly. So if it's not applicable, you have to write down that. If it's like not, if it's not possible to determine based on this data, you can just put X or like indicate that. Okay, so let's start with reading this this plot a little bit more. So here we see like some interesting points, right? So until this point over here, the latency is constant. It is 20 nanoseconds, right? After this point, it starts increasing for strides of 1, 2, 4, and 8. So this is actually showing us the size of the first level of cache, right, of the L1 cache. So when the stride is 1, you basically can access every cache block in the max address region, right? So you have that ability to touch every single cache line because you are just randomly selecting the address. So this stride of 1 is interesting to look at here. Basically, until we reach this point, after running the program long enough, we cache all the data successfully and only access L1 cache. We always have a hit, right? But once we get to 32 bytes, we start seeing cache misses. So the latency increases here when the stride is 1. So this means that we are touching 2 times more cache lines than can fit in the L1 cache. Is this clear? Okay. So this question, in my opinion, is the easiest to solve, but requires a lot of thinking. So once you like understand that, it's very easy to like make those observations and determine like what is the L1 size, what's its latency. But I hope at least the latency is very easy to find, right? So L1 latency is this basically, the point where your like region you are accessing is very small, so it all fits in the L1 cache. This is your L1 latency. Is there a question? Okay, yeah. So basically, let's put that in. So the latency is 20. And here, access latency from is defined as, so it's basically latency that excludes other levels, right? So if, for example, you are filling in L2 access latency, you have to subtract L1 access latency from it. Okay, so this is like just that level, but not through the hierarchy. But for L1, it doesn't matter. It's just 20. And then total cache size. So as I said, you can determine it based on those 2 points, right? So it has to be 16 bytes. Right? If it's small than 16 bytes, then the curve would have looked something like this. So you will have some change in here. Or if it was larger, you can fit more data. Okay. And then cache associativity. So this is a bit more difficult. So how you can tell this is by looking at the other strides. So one thing we see here is that when we increase stride to 16 and the max address to 2 to the 5th, which is like 32 bytes, right? So we have 16 bytes of stride, and we are accessing a total of 32 bytes of a region. So basically, we are accessing only 2 addresses in this case, right? Because we are accessing at 16-byte granularity. So in this case, what we see here is that for 16, we can have like both of those 2 cache lines in the cache. We can fit both of them, right? Because the latency is just the L1 latency here, 20. This basically means we have to have 2 ways in that cache in order to fit those 2 cache blocks, right? Otherwise, since those 2 addresses will map to the same set because the size of the cache is 16 bytes, right? They will discard each other when you access them, but that's not happening. So then the cache is looking something like this. You have two sets, and we don't know how many, we have two ways, and we don't know how many sets we have. So the cache associativity is 2. And for the cache line size, so this is a bit more difficult, but it's not possible to determine based on this information, because like if you test it, you will find that even if you make those like 2 bytes each, and then you have 4 sets in total, it will work. It will generate exactly the same latencies if you simulate like with different strides and different max addresses here. Okay, so basically this is not possible to determine given this information. So another thing to observe from this plot is that there is no similar peaks here, like going up in this plot, right? So if it was like, if there was another level of cache, we would have had a another like straight line over here until some point where we saturate this next level of cache, and then it will again continue rising after filling up that cache, right? So basically, since like it just directly goes to like this latency over here without any such behavior like in here, we can tell that there is no another level of cache, but we directly access the main memory after we miss in L1 cache. Okay, so all those parts are not applicable basically. And the DRAM latency is 100 nanoseconds, right? Because the max point we get is this. So it's like 120 minus 20. And total size, we don't know what's the total size of DRAM. So this is not applicable for DRAM, right? There's no like something like cache associativity, and same for the cache line size. We don't know that. Okay, so like those 4 things are the only stuff that we can say based on this plot. Yep.
So why do we know that there's no L2 cache? Why can't it be like a really big cache?
Sure. It could be a very big cache. Yeah.
Would be also better.
Okay. Yeah.
Because then, like what we said for DRAM, 100 would be in L2.
Yes. Yes. But yeah, maybe you'll be confused in the beginning by that, but after seeing the second part, I think it makes it clear, because in the second part we have, but there again you can claim that you have another level of. Okay, yeah, I think you are right. So, yeah, so you can say that maybe it's a very large cache. Okay, and then this is the second part. So this is the other processor, and you see that here we have more variation in this curve. So we have that like stair-like behavior here, right? So we come to this point, the latency starts increasing. I think this thing is shutting down. Are we over time? I'll just cancel it. Okay. Okay, so we have 2 of those like peaks over here, right? And this basically, like from what we learned from the previous part, we can now tell that, oh, this processor must have 2 levels of cache, right? And then basically in the same way we found the size of the first level of cache, we just look at this point, like the point where the latency for stride 1 starts increasing, right? So that is basically the cache size. It's 32 bytes. And the latency is 10 in this case. For associativity, we do the same, right? So what we did last time was looking at the max address for a stride that can still fit all of its data in the cache. So it is 2 to the 6th, which is 64 bytes, right? With 64 stride. And we see that it can still fit the cache line when it's accessing only one cache line, but once it starts accessing two cache line over here, at this point, the latency increases. So basically, we don't have any room for, so we don't have any associativity here because two cache lines cannot map to the same set. So this is how we tell that we have cache associativity of 1. And the cache line size is, again, not possible to determine from here because of the same reasons. And for L2, it's basically the same that we do, but instead of looking at this part, we are looking at this part now. So stride 1 starts increasing at this point, max size of 2 to the 9th, which is 512 bytes. So this is the size of the next level of cache. And the latencies, so the total latency here is 50, including the L1 cache, but it is asking us only the latency from the previous level, so this is 40 nanoseconds. Okay, and then we don't have anything else here. It is the DRAM, so we know that it is 100 nanoseconds. And yeah, we don't know its size. We don't know anything else here. For the associativity of the second level of cache, we can again do the same. We can look at this point over here, where the for stride 256 and the area, sorry, the max address of 1024, the latency is preserved, right? So this is the L2 latency in this case. So with this stride and this max range, we can fit 4 cache lines, meaning 4 of those cache lines can map to the same set. So to be able to do that, we have to, this cache has to have 4 ways, okay? So the same thing I did here. And again, we don't know the cache line size of the system. So basically, this was the second and last part. Any questions about this? So I think this is a bit difficult to understand. I will suggest you to try to do it yourself again from scratch, although you see the solution now. I think that will help you reason a bit, because reading this graph is not trivial. Okay.
Okay, let's read the question first. An architect is designing a prefetch engine for his machine. He first runs two applications A and B on the machine with a stride prefetcher. Application A and B both are accessing an array A of 1000 UINT 8 element. The only difference between application A and B is while the array indices of application A is incremented by 4, the array indices of application B is multiplied by 4. We know that I and sum are in registers while the array A is in memory. We also know that a cache block is of 4 bytes in size. The first question is, what is the prefetch accuracy and coverage for application A and B respectively using a stride prefetcher? Now, to understand the coverage and accuracy of a stride prefetcher in application A and B, let's first try to understand how many memory accesses application A would generate. Application A would access elements A0, A4, A8, A12, and so on. So this means in total, application A would create 1000 divided by 4, that's 250 memory requests. Out of these 250 memory accesses, the first 2 accesses, which is going to A0 and A4, won't be predicted by the prefetcher because the prefetcher would understand this is the first stride of 4 cache line. Then, once it learns the stride, it can prefetch cache line A8, A12, and so on. In fact, the prefetcher would prefetch the cache line A1000 also, which would be required by the program. So in total, the prefetcher would generate 249 prefetches. As per the formula, we know the accuracy of a prefetcher is number of prefetch which is used by the program divided by the total number of prefetch. As per this rule, the accuracy of prefetcher A, the accuracy of stride prefetcher in this program A would be 248 out of 249, because the last prefetch, which is going to add in element 8000, won't be used at all. Similarly, the coverage of the program, the coverage of the prefetcher is defined as the total number of memory accesses which is predicted by the prefetcher divided by the total number of memory accesses, right? As per this definition, the total number of memory accesses would be 250, out of which 248 would be successfully predicted by the prefetcher. Hence, the coverage of stride prefetcher in application A would be 248 upon 250. Now let's see what would be the stride prefetcher's accuracy and coverage would be for application B. As we can see, application B will access the array element A1, A4, A16, A64, and A256 only. So that means in total, the program would make only 5 memory accesses. But in this case, there won't be a constant stride between these accesses. And as a result, the stride prefetcher cannot prefetch any of the cache line, and the prefetch accuracy as well as coverage both will be 0 for application B. Now let's go to the next question. Suggest a prefetcher that would provide better accuracy and coverage for application A. Now recall that for application A, the stride prefetcher fails to prefetch memory accesses which is going to element A0 and A4, because these are the first 2 accesses which is giving us the stride learning. But a next block prefetcher would always prefetch the next cache block without even looking for a constant stride. Hence, in this application A, a next block prefetcher would actually successfully prefetch 249 out of 250 memory accesses, whereas 249 out of 250 prefetches would be correct. So in this case, the prefetcher's accuracy would be 249 upon 250, and prefetcher's coverage would be 249 by 250 again. So a next line prefetcher would work better than stride prefetcher for application A. Now let's suggest a prefetcher that would provide better accuracy and coverage for application B. Most common prefetchers such as stride, stream, next block prefetcher would not improve prefetch accuracy for application B, as application B does not have an access pattern for which prefetchers are commonly designed. So in this case, some form of pre-execution based prefetcher like run-ahead execution could help improving prefetch accuracy. Now let's go to the next question. Would you suggest using run-ahead execution for application A? If yes, then why? If no, then why not? As we know, run-ahead execution could still provide good prefetch accuracy even for application A, which has regular access pattern. But in run-ahead execution, it might not be possible to prefetch all cache blocks before they are accessed, as run-ahead execution happens only when the application is stalled on a cache maze. So in this case, for application A, a stride prefetcher or a next block prefetcher could possibly prefetch all cache blocks before they are accessed, as prefetching happen in parallel with the application's execution. So for application A, run-ahead execution will not be suitable. But in the case of application B, whose access pattern does not have a regular stride, commonly used prefetchers are not designed to prefetch an access pattern like this. So in this case, run-ahead execution can potentially prefetch some of the cache block. And this is especially true as the address of the cache block in application B does not depend on the data from a pending cache miss. So for application B, we would still suggest going for run-ahead execution.
Okay, this question is about vector processing. So we assume a vector processor that implements the following ISA. We have set instructions to set the vector stride register and vector length register. We have load that loads from memory into a vector register. This takes 100 cycles and is pipeline 100 cycles per load. So if we have a vector length of 100, we will have 100 latency per load, but they are pipelining. We can initialize 1 per cycle. The same for stores. We have 100 latency pipelined, multiply 10 cycles, add 5 cycles, and divide 20 cycles, all of them pipelining. So you assume the following: a processor has an in-order pipeline. The size of a vector element is 4 bytes. The size of the vector style register and vector length register is 10 bits. The processor does not support chaining between vector functional units. The main memory has n banks. And vector elements are stored in consecutive memory addresses. Vector elements stored in consecutive memory addresses are interleaved between the memory banks. So if a vector element address A maps to bank B, the next address, A plus 4, address to the next bank. And N, the number of banks, is not necessarily a power of 2. So the memory is byte addressable. Vector elements are stored in a 4-byte aligned manner. Each memory bank has 4K row buffer. I think this information is not required for this exercise. Each memory bank has a single read and single write port, so that a load and store operation can be performed simultaneously, and there are separate functional units for executing loads and stores. So what should be the minimum? What should be the minimum value of n to avoid stalls while executing loads and stores, assuming a vector of stride of 1? So the latency of accessing one single bank is 100 cycles, so 100 cycles. And we can, one bank will be occupied for 100 cycles. So if we pipeline these operations, we can access the next bank, stride 1, so this is bank 0, bank 1, which this will take 100 cycles, and so on and so on. So we can access this bank again after 100 cycles. So to not stalling the loads, we need 100 banks. So 100 banks, we access one of them each cycle. So in the cycle 100, we will access the last bank. And in the next cycle, the first bank will be already done with the first load. So with 100 banks is enough to stall any, to avoid any stall in loads or stores. Notice that if you have, for example, a load, a vector length smaller than 100, we could have less banks as well without stalling. But here is so we have to assume that the vector length can be any length. So in the worst case, it's 10 bits, as we saw here. So it can be more than 1,000 vector length. So we have to assume that in the worst case. So 100 is the correct answer. Yeah.
Do we assume here that the accesses are in different memory banks? Because if they're all accessing the same memory bank, it wouldn't work, right?
Yeah, they are two different memory banks. So it's specified here, right? Vector elements stored in consecutive memory addresses are interleaved between memory banks. Okay. So the next question is, what should be the minimum value of banks to avoid the stalls while executing loads or restores, assuming a stride of 2. So if we are assuming the stride of 2, if this is bank 0, bank 1, bank 2. So if we assume a stride of 2, the first access will be to bank 1, the second access will be to bank 2, and so on and so on. You have 100 banks, as previously. The access number 50 will be accessing this bank that will be occupied because this takes 100 cycles, right? So 100 banks is not enough for not stalling the load instructions. But if we have an extra bank, you have 101 banks. What will happen is that we access. So in the second let's say in the second iteration, we will, instead of accessing this bank, we will access this bank. So we will be filling the gaps in the second round, let's say, with 101 banks. Yes?
If you have to explain why we say 101, could we also say the GCD of 101 and 2 is 1?
Can you repeat that?
So if we have to explain
Yes.
why we say 101, can we also say the greatest common divisor of 101 and 2, which like the number of banks and stripe is 1? Because I mean that's
Yes. Yeah.
and then full stop and that's okay.
Yes. As far as a reasonable answer is okay. So, okay. Next question is, assume a machine that has memory with as many ranks as you found in part A, so n is 100. The vector stride is 1, and the value of the vector length is set to m, but we don't know n. We don't know the vector length. So, and the machine executes this code. So the total number of cycles needed to complete an execution is this number. What is m? So we can, let's say, draw this code. So the first load, it will take 100 plus n minus 1. It's clear why is this the latency? Have to explain this. This is because, so if we have so if this is one, so we can start one new load every cycle, right? So at the end, we will have this 100, because this is the latency, plus this latency. But this latency is the previous, so if the total one is m, we have 100 for the last one, and then we have n minus 1 here, cycles. We can start one load every single cycle. So we have, so yeah, this is the latency for the load. So the next load, we can start the next load after the first load. It takes the same latency. Then the add. So the add depends on B1. So only if it is independent of B2. So we can start the add here. But as we cannot start two instructions in the same cycle, we need to wait for one instruction here. So we will require one cycle here plus 5 cycles plus n minus 1. Okay, next is the multiplication. This depends on B2 and B3. This depends on the add in the load. So we can, and the last one to finish is the load, right? So we can start the multiplication here. That is, the multiplication is 10 cycles plus n minus 1. And the last is the store. That depends on B4, so we can start after the multiplication. And the store is 100 cycles plus n minus 1. So to know the latency, so we have the latency of this part, so it's 100 plus n minus 1. So this latency is hidden because this is larger. So we have plus 100 plus n minus 1. Then we will go here is plus 10 minus 1 plus 100 and minus plus n minus 1 equal to this latency. And if you solve this equation, yeah, m is 1000. Questions? Yes.
I think this is similar question to what a colleague asked before. The colleague asked before, what happens if two instructions finish in the same cycle? And now I'd like to know what happens here. For example, the vector add finishes much sooner than the vector load.
Mm-hmm.
But we're in an in-order pipeline. So do we assume that we have a reorder buffer to fix the discrepancy of the third instruction finishing before the second? Or do we assume that we just write back and don't care about the in-process exceptions?
Both assumptions are reasonable, right? So
Again, up to me to
yeah. More questions about this one? So, and the last one is so if we modify the vector processor to support chaining, so now we support chaining. So again, it's the same code, right? So we have the load first. We have 100 plus n minus 1. So we have the second load. Second load is independent from the previous one, but we have only one load execution unit. So we have 100 plus n minus 1. You have the add. And the add, where is the add? So the add depends on B1. Depends on this. So because the processor is in order, so we can only start the add after this load. So we can start again one cycle after this load. So we have 5 n minus 1. The next instruction is the multiplication. The multiplication depends on B2 and B3. So B2, so depends on the add and depends on these two instructions. But we can start, because we have chaining now, we can start executing once we have the first element of the two vectors available, right? This is at this point. So when we load, we will have the first element of the load after 100 cycles here. So we will have this before. So at this point, we have already available the first element of the vector. So we can start the multiplication here because now we have chaining. So we can start the multiplication here, that is 10 cycles plus n minus 1. The store depends on B4, that is the multiplication, the result on the multiplication. So we can start the store after the first element of the vector multiplication is is calculated. So we can start the store here. This will be 100 cycles plus n minus 1. So and if we formulate this equation, we have, so m is the value from the previous previous question, so m is 1000. So we have the latency here is so this one plus this one 100 plus 10 plus n minus 1. Oh no, sorry. Plus 10 plus 100 plus n minus 1 equal to number of cycles. And if we substitute n for 1000, the result should be this. Yeah. Any questions?
So this is like typical question in which you have to calculate what's the SIMD utilization. Remember that the SIMD utilization, not only in GPUs but also in vector processors, mean like the ratio of lanes that you are actually using. So here, the first thing that you have is the definition. SIMD utilization of a program run on a GPU is defined as the fraction of SIMD lanes that are kept busy with active threads. When are we going to have active threads? Well, we're going to have active threads when we actually execute some instructions for these threads. The question gives us some piece of code, and this is essentially a for loop, as you can see. And it says that this is going to be executed on a GPU. So the way that this is going to be executed on the GPU is distributing the iterations of this loop across the threads that we have in warps. So here we have n iterations, and these n iterations are going to be executed by a certain number of warps. That's the first question, that's part A. How many warps does it take to execute this program? Please leave the answer in terms of n. So we have n iterations. We know that the warp size is 32. A warp in the GPU consists of 32 lanes, and we also have 32 threads, and we also have 32 SIMD lanes in the GPU. So n divided by 32 is the number of warps, because so in case that n is not divisible by 32, we have to use the ceiling of this division, right? Maybe the last warp is not completely busy, but we will steal this number of warps. Part B says, assume integer arrays A. So we have A and B. A has a repetitive pattern with 24 ones, so it will be something like this, 24 ones, followed by 8 zeros. And B have a different repetitive patterns which have 48 zeros followed by 64 ones. What's the SIMD utilization of this program? So observe that this is the repetitive pattern of A. And A, the values of A determine if the body of this if statement is executed or not. As you already know, this if statement will be converted into some kind of comparison and some kind of branch, right? Because in case that you don't need to execute this body, you will have to branch in order to avoid this loop body. So that's why, depending on what's the exact value that each of the 32 threads of the warp read, we will execute the body of this if statement or not. And observe that here the condition is that A is divisible by 3. Because all these 24 ones that we have here are not divisible by 3. Only those threads that read I equal 0 will actually execute this statement here. So, if we have two instructions, instruction 1 and instruction 2, the first instruction for sure is executed by 32 threads, but the second in each warp, right? But the second instruction, instruction 2, is only executed by those threads for which A modulo 3 is equal 0. That is, for these 8 threads that read these 8 zeros here. So, out of 32 plus 32, that would be the maximum number of threads that we have executed in this instruction 1, and then instruction 2, threads that belong to the same warp. The SIMD utilization in this case is 32 plus 8 divided by 32 plus 32. So this is 40 divided by 64. So that's the answer to this part B. The second part says, is it possible for this program to yield SIMD utilization of 100%? Well, and the answer is yes. But this case in which the SIMD utilization is 100% is going to be dependent on the value of each of the elements of register of array A, as you already know. There are two possibilities here if we want to have 100% SIMD utilization. The first possibility is that all threads in each warp execute instruction 1 and then they go into the body of the if statement and they execute instruction 2. That's one possibility. The other possibility is that the threads in the warp, all the threads in the warp execute instruction 1, but they don't execute instruction 2 because this if condition is not true for any of them. So the answer in this part, if yes, what should be true about arrays A for SIMD utilization to be 100%? The answer here is two possibilities. Every 32 elements is divisible by 3, or every 32 elements isn't divisible by 3. So either way, we will have all threads in the warp executing both instructions or only executing one of the instructions. We are going to stop here because we run out of time. The rest of the exercise is very similar. You already know how you have to reason about this exercise. Here there is a question, part D and E are very similar questions, but the percentage, the SIMD utilization is different. You can reason in a similar way. And the very last part is actually quite easy. This is what we explained in the first GPU lecture about dynamic warp formation. You might remember that there might be a way of, let's say, merging warps like this, where some threads are active, other threads are not active, and if these threads that are active are not in different warps, are not in the same lane, they can be merged, and this way we can have more efficiency in our execution. We stop here. Question says, we define the SIMD utilization of a program that runs on a GPU as a fraction of SIMD lanes that are kept busy with active threads during the run of the program. As we saw in lecture and practice exercises, the SIMD utilization of a program is computed across the complete run of the program. The following code segment is run on a GPU. Each thread executes a single iteration of the shown loop. Assume that the data values of the arrays A and B are already in vector registers, so there are no load and stores in this program. Hint, notice that there are 3 instructions in each iteration. They are clearly marked here in the code. A warp in the GPU consists of 32 threads, and there are 32 SIMD lanes in the GPU. So we have warps of 32 threads, that's the warp size in this case, and the total number of iterations that we have is 1025. So the way that we need to calculate the number of warps is by obtaining the ceiling of the division 1025 divided by 32, and this will give us 33 warps, okay? The only important thing to keep in mind here in this part of the exercise, and also in the rest of the exercise, is that warp number 32, assuming that we start numbering the warps from warp 0, in warp number 32, there is only one single thread active. That's important for the rest of the exercise. For example, here in part B, it says, what's the maximum possible SIMD utilization of this program? Hint, the warp scheduler does not issue instructions when no threads are active. This is something that we discussed when we studied SIMD processors. We talk about, what was that? The density time implementation, I think was the name. When we somehow do a scan operation throughout the mask to make sure that there are at least some threads active before we actually issue the instruction. So in this case, the scheduler checks if there is an active thread. If there is no active threads, then the instruction is not issued. So in this case, how can we get the maximum possible SIMD utilization? Maximum possible SIMD utilization will be the case where all threads in a warp go through the same path. So notice that the first instruction here, instruction number 1, which is this if statement, is going to be executed by all the 1025 threads. Right? So there is no possible divergence there. We are going to have, let's say, 100% utilization for this instruction always. But then there is a possibility that the threads within the same warp diverge, and part of the threads go and execute instruction 2, and another part of the threads go and execute instruction 3. This is not the case that we want to consider, right? The case that we want to consider is where there is no divergence. In this case, we will have maximum utilization. So the way that, or the maximum utilization that we can actually have in this program is going to be 1025 divided 1056. Why is that? Because we only have 1025 threads active out of 1056 threads that exist in 33 warps. So It's impossible to have 100% utilization in this program for the single reason that the last warp is not complete. So that's why we get this number. And now the question is, what should be true in this array A for this maximum utilization to happen? That's what part C asks. Please describe what needs to be true about array A to reach the maximum possible SIMD utilization asked in part B. And it says, please cover all cases in your answer. Observe that whatever the answer is, we will have to give the answer at warp granularity. Why is that? Because the instructions are issued at warp granularity. So divergence is only a problem within a warp. There is no, let's say, divergence. There's no problem in terms of utilization if the threads of one warp go and execute instruction 2 and threads of other warp go and execute instruction 3. So the right answer here is for every 32 threads, they all will go and execute instruction 2 or instruction 3. So which means for every 32 threads, consecutive 32 threads, we will have 32 consecutive values of A which are lower than 33 or greater or equal to 33. That's the answer, and that's what needs to be true for this array A in order to have maximum utilization in this program. Is that clear? If you know, no, that might not be correct. So if you have found that in some question in the optional homework, please put the question in Moodle and we will look at it. Maybe in some of the cases, what you might have seen is that instead of 32 is 64, because in some cases we say that the warp size is 64, but this is just the way it's defined in the beginning of the exercise. The entire array, that might be wrong, but just to make sure, please put the question in Moodle. Okay, next thing is, next part is part D. What's the minimum possible SIMD utilization of this program? So how can we obtain the minimum possible utilization of this program? Well, we already know that this instruction 1 is always going to be executed by all threads, so we are always going to have 100% or 1025 divided 1056 utilization for this instruction. And then what we need is that within each warp, we have divergence. So some of the threads of the warp will execute instruction 2, while others will execute instruction 3. And let's say, I don't know, the number actually might change from warp to warp, but let's assume, because actually this doesn't affect the answer, that in every warp, alpha threads execute instruction 2, and the rest, 32 minus alpha, go and execute instruction 3. So by taking this into account, the way that we can calculate the SIMD utilization is by going instruction by instruction and warp by warp and thinking what is happening there. For the first instruction, we already know that 1025 threads will execute instruction 1 out of 1056 56. And then we have instruction 2, and we know that alpha threads in each warp will execute it. We have 32 complete warps. I'm talking only about the complete warps. We will talk about the last warp with one single thread active at the end. And this is out of 1024, which is 32 times 32. And then instruction 3 is executed by 32 minus alpha times 32 threads, and we divide by 1024. And then we have the last warp. We don't care if this last thread executes instruction 2 or instruction 3. The result is not going to change, but it's only one thread every 32 threads that belong to the same warp. So this, as you can calculate yourself, will be 1025 divided by 1568. And that's the minimum SIMD utilization in this program. The next part, part E, asks, please describe what needs to be true about array A to reach the minimum possible SIMD utilization asked in part D. So what we need to make sure is that there is divergence within each warp. So what we need for every 32 consecutive elements of A, we need part of them be lower than 32 and the other part be, so sorry, I said 32 is 33, and the other part be greater or equal to 33. Okay? For every 32 consecutive elements, such that we make sure that we have divergence within each warp. And then for the last part, F, what's the SIMD utilization of this program? A program where AI is equal to I. Again, for instruction 1, no matter what's the what are the characteristics or what's true for array A, for instruction 1, we will always have 1025 divided 1056. And then we have that instruction 2 is executed by 33 threads. Why is that? Because this condition here, the if statement, is only going to be true for threads with a thread ID lower than 33. So there are 33 threads that will execute instruction 2, and notice that this is the entire warp 0 composed by 32 threads plus one thread in warp 1. And then the rest of threads will execute I3, including the thread in the last warp. So we calculate in the same way as we did before, 1025, 1056 plus 32 plus 1. This 32 corresponds to warp 0. This 1 corresponds to the first thread of warp 1, divided 32 plus 32. And then we have 960 threads that go all and execute instruction 3, 960. And then we have the last warp with one single thread out of 32. And this will give us 1025 divided 1072. Go ahead.
So one question about the divergence. So what's special about this if branch is that, like, I have the
Yes?
And in your lecture you gave, you discussed that there's dynamic warp forming. So in this case, they would be merged to one warp.
Yes.
And then,
well, that's assuming that there is dynamic warp forming. There's this doesn't hold here. Because so this is somehow and actually the way it was explained was like an optimization, possible optimization for warp scheduling on GPUs. If this is not something that real GPUs implement by default, and actually I don't know about any GPU that implements that, real GPU, and if we, decide to, I mean, it would be possible that we have a question like that, but we would explicitly state that case.
yeah. But I mean, okay, but given this exercise is correct if I assume dynamic warp forming, because like in this, like it's really logically, you have like the branch, and in any case, it executes the same number of instructions.
No, you shouldn't make that assumption unless it's clearly stated in the question. So the reasons are, I think it's the second exercise of this type that I solved here in this year, and I didn't consider that in any of both cases. And actually, if you read the questions that we have in the optional homework, that dynamic warp formation is not there. I think, yeah, maybe in some exam some time ago we asked something like that, but it was clearly stated, now consider that there is dynamic warp formation.
So you would say for us in our exam, you shouldn't use dynamic warp?
Yes. So by default, as I said, dynamic warp formation doesn't exist, so you shouldn't consider it. I mean, if someone has the question in the exam, it's the one thing that you can always ask. But
okay. Yeah, I hope that is clear because, yeah.
I mean, it should be clear from now on, right?
Because like also there was once in the homework exercise where like there was a, I don't know, multi-cycle processor, and it wasn't stated if we used pipelining or not. And then in exercise D, like really at the end of the exercise, it said now consider pipelining. So then when I reached D, it was clear, okay, we should use pipelining in exercise A. But if I'm in the exam, I have solved it using pipelining, and then I wasted 10 minutes.
Well, I mean, you're 400 students, and we are only 68, so the variability of assumptions is larger in your case than in our case. And these things might happen, but that's why it's good to ask. Anyway, about the multi-cycle matching, the only thing that I can tell you is that multi-cycle matching, the way that is explained in this course, is never pipeline. Okay, but yeah, feel free to ask everything that is not clear. And maybe one recommendation is also before starting to solve one question, read it completely. Because maybe, I mean, you see how the questions are written, right? Maybe they are very long in the beginning, but then, the different parts, it's very short. So if you read the beginning, then you're not going to spend more than a few more minutes to read everything.
Okay, and if I do any assumption, I will state it.
Mm-hmm. Okay. Yeah, so that would be, I mean, if we tell you, now assume dynamic warp formation in the way it was explained in the lecture, then you will need to worry about the fact that they are in the same lane or not. But maybe another possibility could be lanes can migrate. But in principle, don't worry about that. Anything else? Okay, thank you. It says, we define the SIMD utilization of a program run on a GPU as a fraction of SIMD lanes that are kept busy with active threads during the run of a program. The following code segment is run on a GPU. Each thread executes a single iteration of the shown loop. Assume that the data values of the arrays A, B, and C are already in vector registers, so you don't need to worry about memory accesses. And it gives us one hint. There are 6 instructions in each thread. I will tell you now how to count these 6 instructions. A warp in the GPU consists of 64 threads where there are 64 SIMD lanes in the GPU. And there are 64 SIMD lanes in the GPU. So the 6 instructions are, this is the first one, this if. Then we have 3 instructions inside the first if statement. Then 5th instruction is second if, and this is the 6th, right? Why don't we have to worry about the for loop? Because in the end, the for loop, what is simply expressing is the number of threads that we need to use. This is like the sequential code that we are going to parallelize using the multiple threads that the GPU provides, right? And what the question also says is that each of the iterations is going to be assigned to one individual thread. So we already know what's the total number of threads that we need to execute this program, right? It's 4,096, okay? And this takes us to the first question, part A. How many warps does it take to execute this program? How many warps do we need to execute this program? So the number of warps is the number of threads, which is exactly the same as the number of iterations, divided by the size of the warp, which is 64. And this is 64 warps. This is the number of warps that we need to execute this program, the number of warps of 32 threads each. Because in this particular architecture, the warp has 64 threads. In another different problem, you can find 32, but in the end, there won't be any difference. Okay, so these are 10 points for free, as you can see. Second part is more interesting. It says, when we measure the SIMD utilization of this program with one input set, we find that it is 134 over 320. What can you say about the arrays A, B, and C? Be precise, look at the if branch. So look at the if branch means you have to analyze your code and see what's the influence that the different arrays have on the execution of this program and the utilization of this program. And as you can see, the only important thing to keep in mind with respect to that are the if statements, right? And in the if statements, the only thing that we have is BI. So actually, A and C don't have any effect or any influence on what's going to be the actual path of execution. So simply, we can say, what can we say? We can say nothing about A, and we can say nothing about C. But about B, we can say many things, right? And why is that? Because depending on what's the particular value of B, each thread will go through this if statement or this if or none of them. Why is that? Because there are 3 possible values that are important for BI. 8888, which is we don't execute anything, none of the 2 paths, or greater than or less than, right? So these are the 3 possibilities that we have for the values of B. But now the thing is, how do we reason about what's the actual utilization, which here is 134 divided by 320. So what I would recommend you, and let me use this as a scratchpad, what I would recommend you is that you first start looking at what's the total number of instructions that the program has. And we know that the program has 6 instructions, right? How can we calculate the utilization, let's say, in a generic way when we have 6 instructions? So what we know for sure is that these 6 instructions are going to be executed, potentially, maybe not, but they are going to, obviously depending on what's the actual path of execution, but they are going to be executed by 64 warps of 64 threads. And there are some instructions, as you can see here, that are always executed by every thread. In particular, this one and this one. Why is that? Because we have to evaluate the if statement, right? So this is something that I can already include in the numerator. I know that all the threads of all the warps are going to execute the first, this is the first if, and the second if. Okay? And what about the other instructions? The other instructions are these three and this one. We don't know that, right? We don't know how many threads are actually executing these three instructions, but it is likely that not all the threads inside the same warp execute the same instructions, right? So let's assume that there is a number of threads, X, in each warp that executes these three instructions. And there is also a number of threads, Y, in every warp that executes that sixth instruction. This is Y, it's not 4, just to make sure. Okay? And what the question says is that this is equal to 134 divided by 320. And now we have to think a little bit about the numbers that we have on the paper. If you look at this, so if you look at this expression here, we can get rid of all these 64, right? That's super easy. That's clear. And now, if we look at the denominator, we will see that this is equal to 384. And 384 is not equal to 320, right? Actually, 320 is equal to 5 times 64. Which means that in this particular case, only 5 instructions are executed by any thread. If we go back to our code, the only possible way that this happens, only 5 instructions, is that no one executes this instruction. And this way we will have this one for sure, this one for sure, and these 3. How many threads? I don't know that. But I know that this number is X. Oh, sorry. Okay? The number of threads that execute these 3. So what I need to do here is to somehow rewrite this expression for only 5 instructions. This is 64 times 3 plus 64 times 64 divided by 5, 64 times 64. And again, I get rid of this 64, and this is equal to this. And from here, you will find that X is equal to. Okay? So, right answer here is that 2 every 64 elements of B are less than that. Does it make sense? You can check yourself. There is no other possible answer in this particular question. When we prepare these kind of questions, we usually try that there is only one single possible answer. I'm pretty sure that you can come with other numbers that can take you to different combinations of X and Y, but this doesn't happen in this case. So what, as a general recommendation, what you have to do is to look at the numbers that you have in front of you and reason in that way, because the numbers are usually pretty simple. It shouldn't be difficult for you to reason in this way. Okay? Okay, part C. Is it possible for this program to yield a SIMD utilization of 100%? And the answer is yes. And why is that? Because so what it says, what should be true about A, B, and C for this to happen? Again, we don't care about A and C, we care about B, same as in the previous part. And if you want to have 100% utilization, essentially what you need is that all the 64 threads of a warp which go through the same path, all the 64 threads of a warp always go through the same path. And for that, there are 3 possibilities, indeed. And the 3 possibilities are that every 64 elements of B are equal to 8,888 or are greater or are lower than, right? Every 64 elements. So maybe the first 64 elements are equal to 8,888 and the next 64 are greater and the next 64 are lower. Is that clear? Okay. Every 64 elements will be equal or this or that. Okay, and then last part D, here it is. What is the lowest SIMD utilization that this program can yield? And this is actually very easy to answer. Of course, you would need to calculate the number, but it's very related to what we already discussed in part B, right? Because in the end, in part B, discovered that there were 2 threads in every warp that are executing the same path, right? And this means that you have 2 threads. So if you want to decrease the utilization, instead of 2, use 1, right? And so this way, the way to achieve the lowest utilization is to have 1 single thread going through this path and 1 single thread going through this path. And here you could calculate something like, so the way to calculate the actual number would be 6 times 64 times 64, and here 1 times 64 times 3, which is the number of instructions in the first if, and then 64 times 64 plus 1 times 64 times 1, which is the number of instructions in the second if, right? And the value that you will find here is 132 divided by 384, right? You also need to explain, but you know the explanation, right? Is 1 thread is greater, 1 thread is lower, and the rest are equal, right? But do not forget to explain what you're doing and why are you reaching to some particular result. Any question?
So for this question, we were given basically access pattern, the addresses, so which are basically in byte fashion. So, and the question asks for us, like, we need to come up with the cache design given those access patterns. So so here actually let me explain it first. So basically these are the accesses. So these are the addresses accessed from oldest to young, and then we are given with the hit rates as well. And also these are the sequences of these accesses. But the important thing is that there are no other address accesses between each sequence. Basically these are back to back. So these are the things that we need to know. And for the first question, basically, we need to figure out for the cache block size. So for this one, actually, we can try to do brute force, and then we can try each of the options here. So let's first assume that we have a block size of 128. So if that was the case, then for the first sequence, 0 will be always a miss, right? So this is always a miss. So this is our first miss. But if it is 128, the 4, 8, 16, and 64 will be a hit because this will be located in the same block as in 0. So we have basically here 4 hits, but whereas in the first sequence the question says we have 3 hits because we have 6 accesses and the hit rate is 1 divided by 2. So this won't work. So let's try 64. For this one, again, 0 is a miss. And again, for 8, 16 will be a hit. 64 and 128 will be misses. So this kind of works, okay? So let's try 32 again. So 0 again miss. So 4, 8, 16 again hit, and the rest again are misses. So this also works kind of for now. And for the last option we have 8 and 16, but for these see that okay, 0 will be again miss for both of these, and but for both of these actually we won't be able to include 16. So basically we will end up with at most 2 hits. And this is not gonna work as well, at most 2 hits. So, okay, so we are in between 32 and 64. We need to look at for the second sequence in order to say that, okay, this is the cache size. So for this one, basically, the hit rate is 5 divided by 8. And so we need to first look at those addresses because we basically are sure that those won't be in the same block when they are first accessed. So for the 8K, this will be a miss. Sequence. For the first 8K, this is a miss. For the first 16K, this is also a miss. And for this one as well, this is also a miss. For sure. So these are all misses. So, but again, then the rest of these need to be a hit for us. Okay. So in order this to happen, basically, our cache size need to be 64. Why? If this was 32, then basically 63 would be a miss because we don't basically access any address between 32 to 64. So in order this to happen, basically our cache size need to be 64 so that we will also have this 63 as a hit, all right? So, okay, then 31 and 63 will be hit for us, but here also 64 need to be a hit, but our cache size is 64. But the thing is that, so you need to get this, basically, we previously accessed 64, so this is already in the cache, so this is also a hit as well, okay? So our cache size is basically then 64 bytes, all right? So the second part of the question, so this is basically we are asked to find out the cache associativity. So we're gonna do the same, basically. We're gonna try all of these, like 1 associative, 2 associative. So for this one, actually, we need to consider the total cache size. Okay, it's either 4 kilobase pairs or 8, right? So for this one, if this is 1 associative cache, then for the 4 kilobyte cache, all the multiples of 4K address accesses will be will basically try to access to the index of 0, right? And for the 8K, again, it will try to access to the index of 0 if the cache size is 8 kilobyte. So we need to keep this in mind first. And then let's assume that this is one-way associative. And basically write down all the accesses here. Let's write down all the accesses that are multiples of 4K. Okay. So these are basically 0, I'm sorry, 8K, 16K, 4K, 8K, and 16K. All right. So if this was one associative, so for each axis, we would be replacing the index, basically, index block, right? So, but remember that I'm going to show it here. So those things, these axes, need to be a hit in order to have 5 hits, basically, right? So it cannot be one way. So because those will be removed if it is one way, right? So basically, when I access 8K, it will be replaced with this one, and 16K replaced with this one, 4K. And again, when I access the 8K, this will be basically a miss. And then I will basically replace 4K and then put the 8K. So let's imagine two-way. Then the ways are either 2 kilobytes or 4 kilobytes, right? So basically, I'm going to consider all the accesses of the multiples of 2 kilobytes here. Again, I'm going to do the same thing that I did here. So the multiples are basically the same: 0, 8K, 16K, 4K, 8K, 16. I think I need to write more. 32K. And 8K, I guess. Yeah. Oh, right. This was one. So this is actually, the explanation is kind of similar to the one that I did here. So for the 4-way, actually, you can also consider 63 here. 63 will be a miss as well, because I'm gonna replace 0 with 8K, and then 63 will be a miss, and then this will again reduce the number of hits here. So for the two-way, it's kind of similar. Again, these are the accesses, and for two-way, actually, I will have this one and this one for the first two access, and then I'm gonna replace 16 for either of these, and then again replace 4K for either of these. So this will make us, like, for sure, 8 or 0 will be gone, basically. Actually, both of them, right? So, so when I try to access 8 here, so this won't be in the cache. So this will be a miss again, all right? So two-way doesn't work as well. And one-way also doesn't work. So let's look at 8-way. So I'm going to write all the... So for 8-way, then the size of each way is basically either 512 or 1K, depending on the case size. But basically, we don't know it yet. So each way is 512 or 1K. Then given this, I'm going to basically write, again, all the accesses that are multiples of 512. So these are, again, 16K, 4K, 8K, 16K, 32K, 1K, $8K. So basically, what I did was, so I picked all the accesses in order 0, 8K, 16K, 4K, 8K again, 16, 32, 1K, and this is also a multiple of 1024 and also 8K. So these are the accesses that will map to the same index in this order. So if this was a 8-way, then this would be in cache. Again, this would be, so this is again in cache. So this is already in cache. This is already in cache. So this will be again, that there's a space to put it in the cache as well. So there is also still a space to put this 1K address access into a cache, and also there's a space to put 3K into the cache again, because this is a 8-way associative cache, and all of these actually have the same index, basically. So what does it mean? It means that, so if you consider the sequence tree, so our hit rate is 1 divided by 3. So then this means that I only have 2 hits. So let's first find out the first hit. That is for sure will be a hit, which is 129. Why? Basically, the reason is I already access 128 here, right? So when I try to access 129 here, so this will be for sure a hit, okay? So then we shouldn't, so the options are basically either of these, just one of these should be a hit, not multiple of these, all right? But see if this is an 8-way associative cache, basically I will end up with having 8K as a hit, because this is already in the cache previously, all right? So again, 8-way won't work for us. So then 4-way is our only option left for this one. So the cache size. So we know that this is a 4-way, and block is 64 bytes. And we are asking if the cache size is either 4 or 8 kilobytes. So, so here then the ways are either 1K or the 2K of size, right? The size of the ways are either 1K or 2K, given that cache is either, the cache size is either 8K or 4K again. So then what we need to do is basically, we need to consider actually all of the sequences, but we're gonna focus on the third sequence. So let's again write down all the sequences, the addresses that will map to the index 0, which are basically the multiples of either 1K or 2K. So those will be, again, so we are doing kind of the same thing again and again. This is 0, and this is 8K, 16K, 4K, 8K, 16, 32K. So here comes the trick, basically. So 1K and 3K will map to the same index if the size of the way is 1K. Basically, if the cache size is 4 kilobytes. So this is only possible if the cache size is 4 kilobytes. Okay. So this won't be possible if the cache size is 8 kilobytes. So because it won't map to the index 0. And for 8K, again, it will map to the index 0. So, okay, we know that this is 4-way. Then this will be in cache. This will be put in cache. And then this one, and this one. All right. So yeah, all the ways for the index 0 are full in the cache. So 8K, again, it's in the cache. 16K, it's in the cache. So 32K. So for the 32K, actually, we're gonna, I forgot to write down 0 here. There's also 0 there after 32K, there's a 0. So even if the replacement policy is FIFO or LRU, in either of the case, we're gonna replace 0 for this one, right? So for the 32K is not in cache, and then those are in cache, and then I accessed 8, 16 recently, and also 4K recently. So basically, this is the least recently used, and also this is the first one that put in the cache. Basically, I'm gonna replace this, so this won't be in the cache, and 32 will be in the cache. So for 0, again, this is not in the cache, basically. So what we know is that 0 is for sure a miss, okay? Because remember, we were saying that the number of hits are 2, and 129 is a hit, and then is either 0 or 8K will be a hit for us, and then we now figured out that 0 is also missed. And then 8K, so this one have to be basically a hit. So this will be crucial for us in this question. So why is the case? Because if the cache size is 4 kilobyte, basically this is not in the cache, and this also maps to the index of 0. So basically, I'm gonna basically remove this one or this one. So either of these, if this is FIFO or LRU, the either of one will be removed. So 1K will be put. And for the 3K again, I'm going to replace either 4K again, because this will be the least recently used. If it is not 16, let me see. We access 8K, 16K, 32, and this one, yes. So 4K, either 4K will be removed or 16K will be removed. So basically, what this says is that if the cache replacement policy is FIFO or LRU, basically 8, this 8, address of 8 will be removed along the way. Okay, this won't be in the cache. So why this is important? So if the cache size is 4 kilobyte, and this means that we will have to replace the address of 8K, and then this will mean that the 8K here will be a miss. So this shouldn't be a miss. Why? We are already given with the hit rate, and our only option is 8K should be a hit, and then this means that cache size should be 8 kilobytes, so that those one won't map to the index of 0 in the caches, okay? Not index of 0, so that I will be able to access 8K. So this looks a bit tricky, to me at least. So the last question. So we know that the cache size, is 8 kilobyte. So we know that the cache size is 8 kilobyte. It's 4-way associative, and the block size is 64 bytes. All right, I got through, I guess, yeah. Yeah, let's do the same for the one last time. So I'm again writing all the address excesses that will map to the index of 0 in a sequence. 8K, 16K, 32K, 0, and 8K. And this is 4-way, right? So those are all in the cache. And if it is, yeah, this is 8K, this is in the cache. But if it is LRU, then this is the one that is recently used. So 8K in the cache, 16K in the cache. 32 is not in the cache. So basically, I'm going to replace 0 for the reason that I just discussed in the previous question. So 0 will be replaced, 32 in the cache. So for the 0, so if it is FIFO, then we will have to remove 8. Again, but for the same reason that I described here, 8 should be a hit, then this shouldn't be a FIFO. This should be, the replacement policy should be least recently used, so that I won't remove 8K, instead I will remove 4K, because this is the least recently used, okay? And then this will be a hit. All right, then the policy is Alario. All right, this was mostly oral explanation rather than writing everything here mathematically, but I hope that was clear.